Hello and welcome to the Ideas Vision channel. In our today's video, I will talk about 3D metrology in automation and how optical sensors can supplement the possibilities of tactile machines. After introducing tactile and optical 3D systems, we will focus on optical metrology, about working with point clouds and the requests on resolution and accuracy for doing optical 3D metrology. But first, I will introduce you to our related videos in the IDS Vision channels that are dealing with 3D data. We have one from Martin Hennemann, it's about 3D in machine vision, and another one that deals with the optical 3D sensor using the active stereo technology and unlimited vision with Ensenso. And we have another video about pick and place with robot vision. But now I will start to introduce you some applications that our customers solved with using our 3D optical sensor Ensenso, and see how they solved interesting applications. So in this application, you see the beams of a roof that the carpenters have set up. And before they set up a roof, the beams are moved to the construction site. And the carpenters did a construction drawing, and they order the beams that are cut in the right dimensions in a factory. And to put them together in the right order, they has to be labeled. So in this factory, the beams were labeled manually. So some guy has to write the numbers that are used to correctly put together the beams manually on the wood. And the application now is a system that takes the 3D data from the beams and calculates the place and the font site where a robot then can label the beam without a person having to do this manually. So you can see this in the middle image. All the beams are labeled nicely on the front side, and the right image shows the beam and how it's placed to get the 3D data that is used to calculate the position for the labels. This image shows another application that deals with the assembling of washing machines. Here you see in the middle the concrete heavy weights that are used to make the machine standing firm, even if it's tossing at high rotation speed. And these concrete weights were stacked randomly on a pallet, and now the robot can be used to pick the weight and move it towards the washing machine, and then it's assembled inside. So the workers didn't have to carry along these heavy weights. This is a very interesting application, and I like it very much because it helps to save wood. So it's used to calculate the orientation of the trunk before it's moved into the saw machine. And by getting 3D data all over the trunk, it's calculated in which rotation the most efficient way is achieved in cutting out boards or beams, and this is reducing the waste of wood, so the remaining rest that couldn't be used for the beams or the wood. Now we have seen some applications that are done by using 3D data from optical systems, and next we will have a look at the systems that are providing 3D data. The established 3D measuring system until the 2000s was the tactile measuring machine. it's placed in the measuring room in the factories, and the workers have to move their parts towards the measuring room and wait until someone has the time to put it on the machine and take the measures. On these machines, typically geometric specifications with very small tolerances in the range of some micrometers were checked and against the technical drawing. And to do this, you take the machine takes single points on the surface of the object, and they are used to create primitives like planes or planes or circles or cylinders, and to calculate from intersecting of these primitives the measures. This means that you have to know the objects. So the first part is normally measured with a joystick. You control the machine by moving the probe with a joystick that you use to move the machine towards the points you want to measure. This results in long running time for a complete measuring program. If you have finished your program, you can save it, and after replacing the object with the next one, you can rerun your saved measuring program. So what was missing there was the possibility to get a high resolution on object surfaces. If you want to check a surface of an object that came from a deep drawing machine, like for car manufacturing parts, then you have to take lots of points on the surface of an object to see the form, and this takes lots of time. So with software and hardware, technology is increasing with the years. Since the 2000s, there arise some technologies that allow to get 3D data by using optical systems. The optical systems are way smaller and lighter, and you can move them around, so they are mobile compared to the tactile machine, and they provide a complete surface of your object. The point cloud can be taken from any unknown object because there is no contact between the sensor and the object, so you can measure whatever you want. And the technology is now at a point that the point clouds can be computed in an accuracy and fastness that it allows to even capture moving objects and calculate 3D data from moving objects. Now we have seen the two kinds of measuring systems, the tactile and the optical ones, and we will now have a look at the kind of data they will provide. So first we will look at the tactile machine. If you want to measure this housing of the camera, you would start with getting 4 points on the surface, for example, and calculating a plane through these points. Then you can measure the next 4 points on another side, calculate a plane, intersect the planes, and then you can measure the points on the cylindrical part and create a cylinder. And now you can compare the axis of the cylinder towards the plane or whatever you want. So measuring with this machine means intersecting primitives, doing coordinate transformations, and this way trying to measure all the measures that are given in the technical drawing. When using an optical system, you get all the points at one shot, and compared to the left side where you have 11 points, you have, depending on the sensor you use, maybe you have a 1 megapixel camera, and in the best case you have 1 million points in your point cloud. The difference between the points in your point cloud and the points that are measured with the tactile machine is that the points on the point cloud doesn't have the same high accuracy in 3D position on the surface as the tactile machine provides. So you have lots of points, but as you see in this image, not all points are really located on the object surface. So if you want to do any measurements in the point cloud, you first have to remove points that are not actually part of the object. And then measuring in a point cloud can be reduced to just the same thing that the tactile machine does. So you choose an area in the object, in the point cloud, and fit a plane in the top plane of the camera, and then intersect these planes, or you fit a cylinder in the front part of the housing, and then you have the axis of the cylinder by fitting the primitive into the points. So as you see, this camera is not completely covered with points. If you want to have a complete point cloud of an object, you have to take several views of the object and then calculate one complete object from this single views of the point cloud. Now I will show you what's the benefit of getting complete surface data in points. So in the left image, we have in gray the 3D CAD model of the camera housing, and in orange, the points of the point cloud. So you see there are some areas in the point cloud that are not part of the object and some that fits very well. And here in this image on the right side, I used MVTech's software Helken to calculate the distances between the points and the surface of the CAD model. And the color is coded from the smallest to the largest distance, and you can see the points that are close to the surface are marked with red color, and the points that have the largest distance to the CAD model are marked with blue color. And this way you can track how good does the form of my object is like I want it to have. So for example, if you have a deep drawing, a tool in the factory for automation, for manufacturing cars, then this way you can see or improve where you have to do changes on your tools to achieve the needed form of your object. Another way of using this complete surface would be to mark in the point cloud areas that are different to the model. So in the left side of the image, you see the point cloud that is taken from a small model of a car. And here you see the complete model. So this has been created, this point cloud has been created by rotating the car, and I guess it was about eight captures, so that this point cloud is combined by 8 single parts of the object. And then it's smoothed, and this is the result. So this is not what you actually get out of your sensor. This is done by removing all the parts that are not the object, and then you get a point cloud like this, representing the shape of your object. And now you can compare another object, whether this looks the same as you saved your model. And for example, here you see the wheels changed. They are wider, or on the spoiler there is a red part which we put on before capturing the data to show the capability of the software to identify things that are different from the model. So this can be used for assembling jobs. If you have a master system which you use for a model, and then you can, after assembling your parts, you can compare your scene with your master and can easily check whether everything is in place and whether you use the right parts for assembling. In this image, you see a box with rings, and on the right side, the point cloud taken from this scene. So you can use the point cloud here for example, if you want to separate the rings, you see that the rings are not the same. So you can identify them by comparing the point cloud and the cut model of different rings, and then you can say this is every type of ring should be placed in a different location. And of course, if you want to grab the parts with a robot, you have to find out the location of the objects in the box to make the robot able to grasp the part. And as you can imagine easily, this is not a job that can be done by a tactile machine, because the tactile machine doesn't know what is this type of ring. So it doesn't know where to move to with its probe, and it doesn't know where is the ring located. So this is a classical example for using optical sensors. In the next image, we see a 3D point cloud from a piece of metal that's angled, and there are 3 cutouts that are bent above. And by sophisticated algorithms, you can cut the point cloud and do some measurements in the lines you see on the right side of the image, so you can check whether the bends are in the needed angle or not. So this, of course, is you can do this with sophisticated algorithms you find in image processing software. This image is also taken from an MVTech Helken example, and you can see this is not a point cloud. It looks like it has a surface, and this is also a thing you can do with point clouds. You can triangulate them and this way create a surface on the points, and then you can use it as a 3D model. For example, if you do not have a cut model of a part, for example, you could use this triangulated point cloud instead of a cut model for matching purposes. If you want to find the model, to use the model for 3D matching, you can create your own models by triangulating a point cloud. Then it looks like in this image. So now I've talked about measuring in point clouds, but if you want to measure something, then you have the question, what is the accuracy of my measuring system? To check the measuring system's accuracy for optical systems, there are important question is how true is the form of my object to represent it in the points, and how accurate is a length measurement, and what's the if I measure with my sensor on a flat plane, does all the points show the same coordinate in Z? So for checking this, you can use a reference object like this dumbbell here, and you can create points on the spheres, and by fitting a primitive, a sphere, into the point cloud, you can measure the distances of your points towards the sphere primitive, and you can measure the distance between the 2 spheres center, and this way you get you get to know how accurate your distance is. Of course, this is not just a simple example, a reference object has been measured on a high accurate measuring system before, that you know exactly the diameters of the spheres and exactly know the length value between the two centers, and then compare your 3D data against this reference object. And to get an idea about the measuring accuracy for set values, you take a measurement of a plane, and the points will be distributed between these two blue planes that are in the image. And then you can see the smaller the distance between these two blue planes, the more accurate, the higher is the accuracy of your 3D sensor in providing set data. So now let's have a look on how to adapt your optical sensor to your needed object and to your needed measurement volume. I'll start with explaining something related to the camera sensors that are used. So, as I mentioned, you have very much points on the surface or around the surface of your object, and you're not sure what is noise and what is really the object. So before you use your points in the point cloud for doing some measurements, you have to use a noise filter. And if a part of the object is only covered by one single point, this point is likely to be killed by the noise filtering. And everything that should survive the noise filter should be should contain some more points than only one. So if you want to have a structure on your object to be visible or to be measurable in your point cloud, be sure to have at least 3 to 7 pixels that are covering this structure to be able to find it in the point cloud. So in this example, if you want to measure the size of this green square, you should select a camera sensor that has a pixel size of the length of the cube divided by 3 or 4, and then you're sure that you have enough pixels to see this face of the cube in your point cloud. Adapting different measurement volumes means, so if you look at the image, you see the cameras are mounted with different angles. If you want to use two cameras and create 3D data by comparing the two images, then you have to be sure that your object is covered by both sensors. So your left and your right camera has to see the object to be able to provide images that can be used for calculating set values. And if you look at the image, you see the left combination, the intersection of the cameras is very close to the camera, and by moving the cameras with more parallel direction, the intersection is moving in a distance far away from the camera. So this way, by changing the angles of the camera, you set the distance, the working distance, where you can place your object and have a good overlap between the two images. And the height of your measuring volume also depends on this overlapping area, because I show you in the next image. So if you see the largest area, it's about 4.5 meters. This is possible to be measured if it's not too high, because if you have this area maybe with a height of 1 meter, the top plane wouldn't fit in the overlapping area of your two cameras. So if you reduce the area, like the middle square in this image, then you can have a height of your measuring volume of about 2 meters. And the very, very small object on top of the middle cube is a small cube with a size about 5 times 6 centimeters, and the camera is about 40 centimeters above the object. And with this setup, you're able to achieve high accuracy in set measurements of smaller than 1/100th millimeter, whereas the large area and the camera hanging about 5 meters above the object will reduce the set accuracy to about 6 millimeters. So you can change your measurement volumes, and of course the accuracy changes with the settings. Here we have an example of a small measuring volume. These are two connectors that are placed on printed circuit boards, and you see the white areas to the left of the connectors. They are caused by the shadowing because the right camera wasn't able to look at this part of the image. The image you see on top of the 3D data is the left camera image, and the right camera image looks a bit different. And on the right camera image, this area is missing, and so you have no 3D data. This is shown in white here, where you have no data. And you see the red points are showing the connector, and the white squares inside, they are because the pins are very small and they are reflective, and this is a challenging challenging surface quality. If you have reflections on materials, they are likely to be not matched or wrong matched, and thus you have data that is missing or that you cannot use. Here is the opposite of a small measuring volume. You have a very large measuring volume. You see in the green circle, there is the camera mounted on top of the robot. And this is an application that stacks large boxes onto a pallet. And maybe you ask, why do we need 3D data here? The robot can be programmed to put one box close to the next. That's true. The robot doesn't need 3D data to stack boxes here, but you want to check if the calculated place for the next box is currently free. So maybe there some box fell or was misaligned, and then you are not able to put a new box in this place. So you check the free space before moving a box to this position. So the high computing capabilities of our today's computer hardware and software allows to generate point clouds at a high frame rate that allows inline measurements and measuring object positions, maybe on a conveyor belt. So you're able to check the ongoing production, and you get one step closer to 100% control, which because you're not take your objects and carry them to the measurement room, but you can directly use your camera and check the objects while production is going on. And for example, you can sort some objects out, or you can say this has to be remanufactured, and this way you help reducing wrong parts being delivered to customers or being assembled, and 10 steps later you see, oh, I have to remove this part. So I will summarize with an overview for typical applications for optical 3D sensors. So you can use optical 3D sensors for distinguishing different objects that are thrown together in one box. If you want to separate them, you can provide data for tactile measurements. For example, you can adapt the path of your tactile machine by evaluating the 3D data of your optical system. You can determine object poses for grabbing the objects with a robot. And because of the high frame rate that is available, you can use the optical 3D systems for inline inspection of objects. If you want to buy an optical system for your application and you have questions about what accuracy do I need, which cameras do I need to put on my system, how can I adapt the optical sensor to my measuring volume, what's the set accuracy this system achieves, what does it cost, what frame rate can I expect, feel free to contact the vision consultants at IDS. They will help you to find a suitable optical 3D sensor for your objects and your application.